All right, good morning. So last time we actually came to a point where we found a way of solving essentially differential equations by a way of looking at a catalog of responses. And again, to refresh everyone's memory, I'm going to go over that just to, since it's very important. So remember we said, generally speaking, if you have a system, an LTI system, with an input x of t and an output y of t and h of t as the impulse response, and we know that we have a system operator, h capital H of p, that generates y of t off of x of t, right? So this operator operates on x of t, produces y of t. But we then said that you could also express the inputs and outputs, the waveforms, in terms of an operator. And the way we did that was by saying that an input and output, an arbitrary waveform, can be generated off of an impulse, which we knew had some interesting properties. We tried to generate everything off of that, and using an operator. So it's basically, you could say our x of t, we expressed it as capital X of p, the operator x, operating on the delta of t. And the same thing for y of t, where we had y of p operating on delta of t. And then we saw that obviously plugging this into here and looking at that, you saw that y of p, the operator associated with y of t, the operator that produces y of t off of a delta, is essentially the product of the system operator and the input operator. So we call this the input operator, this is the output operator, and this is the system operator. So this is the system operator, input operator, and output operator. Okay, so anyway, looking at that, what we see is that it does something very interesting, because we already knew another relationship. We knew we knew how to calculate y of t. If I gave you a y of t, an x of t, an input signal, and an impulse response for a system, how did we calculate y of t? The convolution, right? So it was h of t convolved with x of t. So these are basically duals of this thing. So this is an operator domain. You see that the convolution in time domain turns into a multiplication in the operator domain. It's very powerful, because again, convolution was not a very simple operation to perform. Though it's an important one, understanding it is very important. And that's why we started with that. Because if you don't develop a good intuition for convolution in time domain, then you will lose some insights, particularly when it comes to design. And you've seen some of these in your problems, that when you try to, for example, generate a certain input that produces a certain output and things of that sort. Right? Anyway, so that was an important conclusion that we had. And then the way we said we deal with this was to basically we created a catalog of x of t's and their associated x of p. In other words, the operator that generates x of t off of an impulse. And we saw that if x of t is delta of t, the operator is 1. If it was u of t, the unit step, the operator was what? 1 over p. For t u of t, which we also show as ramp function, r of t is 1 over p squared. In general, we said if you had a tm over m factorial u of t, it was 1 over p plus, 1 over p to the power of m plus 1. And then we did other ones, right? We said an exponential e to the negative rt u of t was 1 over p plus r. And we did all of these things. We derived these things. I'm just like restating them for for the rest of the stuff we are going to be doing. So then we had also cosine of omega 0 t u of t, and sine. Cosine gave us p over p squared over omega squared, and sine u of t gave us omega 0 over p squared plus omega 0 squared. Then we had even the more complex ones, e to the negative sigma t cosine of omega 0 t u of t, and e to the negative sigma t sine of omega 0 t u of t. We did all of these last time, so I'm just reviewing it very quickly for you. And we knew from these, for example, so this became p plus sigma over p plus sigma squared plus omega 0 squared, and this became omega 0 over p plus sigma squared plus omega 0 squared. So we did all of this last time. So none of this is really new by itself. The other thing that we did, which was also interesting and important, was the delay function. So we said that if you had if you're looking at x of t minus tau, we did it for h, but it doesn't matter, it's any function, right? The associated operator, so in the operator domain, what does that look like? So if you think about x of, so for the same kind of similar table, what does this correspond to? We did the derivation last time. And this was an important one, the delay, the time shift. What did it correspond to in the operator domain? e to the negative tau p x of p would generate this function off of delta. So for any arbitrary waveform, delta of x of t. And then we know what this function means, right? I mean, really, this is a series, right? Exponential is a series. E to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial. So it's just basically a way of a compact form of writing that series, as is the exponential, right? So those were some of the important things, and we saw that we could solve problems with it. For example, you could do convolutions, things of that sort. So, for instance, if I gave you a function like this, let's say if I say my impulse response is like this, it looks something like this. Let's say it goes to, let me just use a different color. So this is versus t. So this is 1, 1. Let's say, I don't know, this is like, 3. So this is your impulse response, and this is, let's say, your input. Let's make something up. X of t. So let's say it's a u of t. Make things simple. So x of t is u of t. H of t, we can write it as a combination of singularity functions, right? Well, how can we write it? What is it? It is, so if you look at just this part of it up to here, what do you see? You see just the ramp function, tut, right? And then you need to take another ramp, subtract another ramp from that. So you can write it as r of t minus a scaled down version of a ramp, right? So you need to first subtract. So at this point, if you want to just start becoming flat, what did you need to subtract? R of t minus 1, right? Right? Do you see it? I'm expressing this, expanding this as this plus that to get, if I wanted to get it flat. But I don't want to get it just flat. I wanted to actually make it a little bit steeper. So I have to make it a little bit larger. So what should this coefficient be to get that? What is that coefficient? The slope is 1/2, right? So it's now, what is that coefficient? 3/2, right? So that produces, but that keeps going, right? That keeps going down. So I have to stop it at that point. I need to do what? Add a r of t what? T minus 3. And what's the coefficient? 1/2, exactly. Thank you. So I can write it this way, right? So that's the input. And the, oh, sorry, that's the impulse response, not the input. That's the impulse response, h. And the input is simply u of t. So this is another example, right, we are doing. So now we need to write the equivalent operators for these. So how do we do that? Well, we can use our rules and the catalog, the table, right? So help me out. What is the first term? What is the term associated with this? 1 over p squared. What is the term associated with this? What would it be if it didn't have the delay? It would be 3/2 1 over p squared, right? So now what is it? It's going to be that times an exponential. E to the minus p. And then the last term is, again, 1 over p squared, e to the negative 3p, right? We good? So that's the operator associated with this, with the impulse response. There's an operator associated with the input, which is x of p, which is simply 1 over p, right? Up there. So now, if I want to find the output for the system, there are two different ways to go about it. Now we have two completely different ways of doing it. I mean, they're fundamentally the same, but there are different ways of calculating it. Which is what? One is the convolution, right? So you just basically slide them, flip one slide across, look at the area of the product, the overlapping part, and then calculate it as a function of t, and then that would give you the answer. And you've done similar things several times. You should be proficient in it by now. That's why we are moving to the next thing. Now, so then, but in this way, we can do it much more simply. We can actually use this way of calculating, which is the product. And the product is pretty straightforward to calculate, right? So y of p is this times that, which makes it 1 over p cubed. It's simple. I'll keep it for myself. I'll give you the difficult ones. Okay? Am I missing something? So now, so now this is y of p. This is the operator. If this operator operates on an impulse, it generates the output. But we don't even need to do that, right? Because now we can actually reverse it using these terms. And one more thing, which is basically the underlying assumption to all of these things, which comes from this L. The linearity implies the standard issue answer. Superposition, exactly, right? Because you can deal with them independently. Right? So, okay. So what is the response? So what is y of t based on this? So what does 1 over p cubed correspond to? What kind of input, what kind of time domain waveform does it correspond to? What is it? T squared over 2 u of t, right? Minus 3/2. Now, what is this? Well, you know how to deal with these things. These are actually basically just, from a practical from a kind of computational perspective, you can think about these exponentials as just ways of keeping track of how much you need to delay. And the multiplicative effect, which basically just adds the delay, the multiplicative effect of exponentials, which basically adds the arguments, will produce the added delay. So essentially, it's the same thing, same function, 1 over p cubed, delayed by 1 second. So it would be exactly the same function where you replace the t with t minus 1. So it becomes t minus 1 squared over 2 u of t minus 1. And the last term is going to be the same argument except for the fact that it's delayed by 3. So it becomes t minus 3 squared over 2 u of t minus 3. So you can see it's a lot, probably, I mean, depending on how you think about these things. But if you know what you're doing, it's a lot less work. But in reality, whenever there's something that you see something is much less work a certain way, it's because the work has been done somewhere else. Right? Or either you have already done the work, or somebody else is doing the work, or some machine is doing the work. When you see something is less work, it's the machinery that you have created. It doesn't say it's less useful, but you have to realize that you just basically are reusing all the machinery that you have already spent a lot of time creating. But the good news about this thing is that the machinery is there, you can reuse it. It's like an algorithm, right? Same thing happens with humans.
Is work conserved?
Well, isn't it? Isn't it called conservation of energy? Work is conserved. Yeah. Yeah, but there are certain, but there's, in addition to that thermodynamics, first law of thermodynamics, which is conservation of energy, there's a second law of thermodynamics, right? So the question was, does that mean the work is conserved? Work is conserved. And I basically played on the word and said that, yeah, it is because it's conservation of energy. But if you take that very inaccurate or rough analogy, there's the second law of thermodynamics, which means that not all sorts of energy are equal, right? I mean, they are equal, but they are not all equally useful. There are different, some kinds of forms of energy are much more useful than others. And there are certain kinds of work that are much more useful than others. I could embark on counting the number of grains of sand on the beach. That would be a lot of work. It's not necessarily useful. The same way that it would be hard to extract useful work out of just a thermal energy of some object, because it's a high entropy state. Anyway, so before getting too much into the humanities, let's stay on track. All right, any questions on this? Okay.